In this video, we solved problem number 4 from Differential Equations quiz number 3 from the spring 2021 semester. There were multiple forms of this quiz, so you may not have seen this particular version of this problem, but basically this is a choosing the appropriate method problem, and we're dealing with first order differential equations. So the problem statement says, for each of the following differential equations, identify a method that may be used to solve the differential equation and then justify your choice. More than one method may be appropriate, so there may be more than one correct answer. You only need to write down one of the correct answers, not all of them. Write each DE in the form of a separable DE, a first-order linear DE, a homogeneous polar DE, a Bernoulli DE, or an exact DE. If you choose any of the last three methods, do the necessary calculations to show that the chosen method applies to not solve the differential equation, but I do want you to outline the method. Okay, so when I look at this, and I'm thinking through my methods, I don't think that it's separable. If I get dy dx by itself, let's see, watch what happens. If we subtract this expression from both sides, we have this. And then if we divide both sides by dx, and divide both sides by x, we get this. So the x's reduce, and the dx's reduce. And now we have dy dx equals this expression divided by x, or you could just divide each of the terms by x. So you have negative secant of y over x. This divided by x is just going to leave me with the secant, and then we'll have the y over x over there. Well, this is clearly a function of y over x alone, so that makes this a homogeneous polar differential equation. So this is equal to negative secant of v plus v, where v is equal to y over x. Okay, so let's answer the question. It says, identify a method that may be used to solve the DE. Well, it is homogeneous polar. So we'll say that this is a homogeneous polar DE. You're asked to do the necessary calculations to show that the method applies. So one version of that is what I just did. So I wrote this as a function of v, where v is equal to y over x. I wrote dy dx as a function of v. So that's one way to handle that part of the question. Another way is to show that this is a homogeneous function of degree 1 and x is a homogeneous function of degree 1. And so the differential equation is homogeneous polar. That is fine as well. So that's one potential calculation. So you can do this, or you can do this. I will call the function multiplying dx m of x and y. I will call the function multiplying dy n of x and y. And then I will evaluate each of those at tx and ty and show that you just get the original function times the power of t. That's another way to confirm that this is homogeneous polar. So m of tx and ty just comes from replacing all of the x's with tx and all of the y's with ty and then simplifying. So x is replaced by tx, y is replaced by ty. And of course, these t's reduce here. And then if we look at this as a term, and this is a term, using term in a looser sense, these two terms have a t in common. So we have t times x times secant of y over x plus t times y. If I factor out the t, I have that. So that's t times this function, and that is the original function m. So that's m of x and y. So that means that m is a homogeneous function of degree 1. Okay. Now, n is much easier. It's just x. So if I replace x with tx and y with ty, if n was just x before and I replace x with tx, I just get tx. So that's t times the original function n. So it's t times n of xy. So if this expression is t times n, then n is a homogeneous function of degree 1. Since these are homogeneous functions of the same degree, and the fact that they're the same degree matters, the differential equation is homogeneous polar. Okay. That's one way of doing it. You don't have to do both this with the 1 star and that with the 2 stars. Just one of those would be fine. And the third option would be to show that the function in the numerator here and the function in the denominator there are homogeneous functions of the same degree, which is the same as showing that m and n are homogeneous functions of the same degree. Notice that n is in the denominator and negative m is in the numerator. That's always how that works when you get that dy dx by itself and you think of this on the right-hand side as a quotient. Okay, so we're asked to identify the method and then do any algebra or calculations to show that the method applies. We've done that. And now we want to outline the method. So the question is, well, how do you solve a homogeneous polar differential equation? Well, first we write the dE in this form. dy dx equals some function of y over x, or it could be x over y, but we tend to use y over x. Then we let v equal y over x. That means that y is equal to x times v, where v is a function of x. And then we can compute dy dx using the product rule. So we'll have derivative of the first, which is 1, times the second, plus derivative of the second, which is dv dx times the first. And then you substitute. So you're going to replace dy dx with v plus dv dx times x. And again, that comes from the product rule. And you're going to replace y over x on the right-hand side of the differential equation with v. That is going to cause the entire differential equation now to be written as a new differential equation in terms of v and x. So you could also say, instead of specifying this replacement, you could say, write the dE in terms of v and x. And if somebody says, how do you do that? This is how you would do that. That will always be a separable differential equation after you do that. So then you're going to solve the separable equation. And then finally, you will back substitute. So you're going to have an expression involving v and x, but you want an answer in terms of y and x. So you're going to replace v with y over x. So you'll have a final answer in terms of y and x. If it's possible, we typically solve for y. And not just possible, but usually if it's a relatively easy, we'll solve for y. And if we can't, we'll just call it an implicit solution and be done. Okay, same question, new differential equation. All right, so we have this. Well, if I factor out the y here, I can write that as 3 over t times y. Well, that's just dy dt plus a function of t times y equals a function of t. So that's first order linear. Or you can say it's a first order linear ODE. The method is to solve with an integrating factor. And how do we do that? First, we write the DE in standard form. And then we're going to find our integrating factor, which requires identifying P and computing its antiderivative. Then the integrating factor is e to that power. You choose the constant of integration to be 0 because we only need one integrating factor, not infinitely many integrating factors. Then we multiply the DE by the integrating factor. When you do that, the left-hand side will be the derivative with respect to your independent variable, in this case t, of y times the integrating factor. And that's nice because that means you're 2 steps away from getting y by itself. To get rid of the derivative, you want to anti-differentiate both sides with respect to t. It's obviously both sides because you don't want to change one side, not the other side. And then you'll have y times the integrating factor equals some function of t. So you'll divide by the integrating factor to isolate y. Easy breezy. And it's okay if it's not an easy breezy process at first, but after a little while, a little bit of practice, this will come pretty easily for most students. It's such an important method, and so many other methods simplify to this method. You make a substitution and then it's first order linear. It's an important one to learn. And I think it's really important to understand why it works. We don't want to just memorize formulas, but we want to understand that Bernoulli said if you multiply by e to this power, then the left-hand side is the derivative of a product. And that means you can get to y pretty easily. Okay, so that's for that differential equation. Let's look at another one. Okay, so this is the third differential equation. Notice that x is not the independent variable this time, it's the dependent variable. So we're thinking of x as a function of t. And I notice I've got an x to the first and an x cubed. So I'm thinking Bernoulli. So let's subtract this term from both sides. Let's factor out the x from that. So we'll have 1 over t times x there. And that's what you have. So we've got dx dt plus a function of t times our dependent variable x. And then you've got a function of t times our dependent variable x raised to the nth power. So this is Bernoulli. Now, I know that's an x to the n instead of a y to the n, but x is playing the role of y. It's the dependent variable this time. So this is a Bernoulli differential equation. So this is a Bernoulli dE with n equals 3. Now here's the method. Actually pretty easy. After we write the differential equation in standard form, we let u equal y to the 1 minus n, or excuse me, in this case it's going to be x to the 1 minus n. And we compute du dt. So that'll be the derivative of this with respect to x. You have this power minus 1, 1 minus n minus 1 will just be negative n, times the derivative of the inside by the chain rule. X is a function of t, so the derivative of the inside is dx dt. After you do that, you're going to multiply the differential equation by that. If you would rather that this be more concrete, you could say let u equal x to the 1 minus 3 or x to the negative 2 Therefore, du dt would be negative 2x to the negative 3 times dx dt. And that dx dt, again, comes from the derivative of the inside. It's like implicit differentiation from Calculus 1, or you can think of it as a chain rule. So you've got that. Now you're going to take your differential equation in standard form. I guess we needed to put that here. Step 0 is to write the dE in standard form. You're going to take that differential equation written in standard form and you'll multiply by this expression here. After you do, you want to simplify. Then you want to write the resulting differential equation as a first order linear ODE in the variable u. You'll always be able to do that because you'll have an x to the n, and when you multiply by this, you're going to have an x to the n times an x to the negative n. When you add the exponents, you get x to the 0, so that piece of the n will be gone. So you'll end up with a first order linear equation in terms of the new variable u. Now you want to solve that with an integrating factor. And then you want to back substitute. Or in other words, you want to replace u with whatever it was in terms of x. The original x was x, or u was originally x to the 1 minus n. Typically we see u equals y to the 1 minus n, but our independent variable was different this time. Okay, and then you just solve for x. Again, we're solving for our dependent variable. Okay, and that'll involve raising both sides to the reciprocal power. It'll be raising both sides to the 1 over the quantity 1 minus n power. Okay, so that was our, what was that, third differential equation? Let's see, let's look at the next one. Okay, so we've got this guy. Right away, I see that I can write this as 1 over y cubed times x cubed over the square root of x minus 1. So that is a product. That is a function of y times a function of x. If you can write the derivative as a product of a function of y and a function of x, or a function of the dependent variable and a function of the independent variable, then the differential equation is separable. So the dE is separable, so the method would be to separate the variables. Now you were instructed to do some kind of calculation to show that the differential equation, that this method is appropriate. So this would be sufficient for that. Another thing that you could do is you could actually separate the variables by multiplying both sides by y cubed and then multiplying both sides by dx. And then we would see that the variables are separated. Either one of those would be fine. So the method is actually really simple. We just separate the variables. X is on one side, y is on the other. Make sure your dy and your dx are in the numerator, not the denominator. Otherwise, the integrals won't make sense. Then you just want to anti-differentiate both sides with respect to the variable on that side. And then after you've done that, you have an implicit solution. If possible, you want to solve for y to get an explicit solution. Okay, easy breezy. And we've got one more. Okay. So let's think through all the methods that we've discussed. We're looking for separable DEs, first order linear DEs, homogeneous polar, Bernoulli, and exact. Now we've already covered the first four. The last one is probably exact. But let's say that we didn't know that. If we're looking at this, you might say to yourself, how can I tell that it's exact? Well, we can't necessarily, but we do see that it has this form of a function of x and y times dx plus a function of x and y times dy. If I call the first function m of x and y, and I call this second function n of x and y, I could take the appropriate partial derivatives and see if those derivatives are the same. If they are the same, then the differential equation is exact. So let's compute the partial derivative of m with respect to y. Now, the label m and n, those two labels, they don't really matter. What matters is that you're taking the derivative of the function that is multiplying the dx with respect to y. That's because this function is, if the differential equation is exact, this is the partial derivative of the original function f with respect to x. So when we take this derivative, we're seeing if the mixed partials are equal. If the partial of f with respect to x or y, x and then y is equal to the partial derivative of f with respect to y and then x. That's what this is all about. Okay, if you don't remember that, that's okay. But the point is, the function that's multiplying dx, you want to take the derivative of that function with respect to y. I'm labeling that m, so that's represented by this symbol. Partial of m with respect to y is equal to this. And it's actually pretty simple. X is a constant. We're treating x as a constant. So this is the derivative of a constant times y. The derivative of a constant times y is the constant. And I also have a constant times y here. The derivative of this constant times y is that constant. So we have e to the x plus x e to the x. Okay. And I want to compute the partial of n with respect to x. That's my first function, and that's my second function. According to the product rule, we'll get derivative of the first times the second, plus derivative of the second, which is e to the x, times the first, plus the derivative of 2, which is 0. So e to the x plus x e to the x, those are the same. So we've got these two partial derivatives, and they're equal to each other. The DE is exact. And that way we solve an exact differential equation is the following way. Once we know that the differential equation is exact, that implies that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n for some function f that we need to find. In order to find f, we're going to do the following. So first we compute f this way. We take the partial of f with respect to x and we anti-differentiate with respect to x. And remember, this is actually equal to m. So we compute that. That's not going to recover f completely. It's going to recover f partially. We're going to end up with a function plus some arbitrary function of y. Or it's actually not arbitrary. We're going for some unknown function of y. It's going to recover everything but that function of y. In order to find that function of y, we do pretty much the same thing, but rather than starting with the partial derivative of f with respect to x and taking the antiderivative, we take the partial derivative of f with respect to y and take the antiderivative with respect to y. Now this is actually n. Now this is going to recover f partially as well. It's going to be some function of x and y plus some function of x. Those have to be the same. because the differential equation is exact. So we're going to compare the answers from 1 and 2 to find f in general. And then the solution, and it's not general solution, I guess it's a family of solutions. It's a level curve on some function of 2 variables. It's given by f of xy equals some constant. And I've been calling that constant k, but you could call that constant c. Okay, so that is how we solve these problems. The idea is that you would recognize which solution method applies, and then you would know how to go about solving similar problems. You don't have to solve these problems. You weren't supposed to solve these problems. That would take too long. But you were supposed to be able to outline the method for me. That when you see an exact equation, this is what you do. Or when you see an equation like this, it's separable, this is what you do. Or a Bernoulli equation, or a first order linear equation, or a homogeneous polar equation. So that is the answer, or a version of the answer for problem 4. There may be other correct answers, although I didn't see any differential equations that could be solved using more than one method. That doesn't mean that one of these other equations isn't separable. It doesn't mean that's necessarily true. This is just one way of solving these problems. If you came up with another way that's also correct, of course, you'll get full credit for that.